Hey everyone, and welcome back to Learning Hub, where we turn complex tech into simple bites. Ever wondered how a chatbot seems to understand your rambling thoughts? Well, that's often thanks to the magic of recurrent neural networks. But before we dive in, here's a brain tickler for you. What do RNNs and a forgetful goldfish have in common? Stick around and you might just find out the answer. Or maybe not, like goldfish. In our previous videos, we unwrapped the concepts and the math behind RNNs. If you missed those, I highly recommend checking them out. Today, we're getting our hands dirty and building an RNN from scratch using NumPy. First things first, let's import NumPy. If you don't have it, install it using pip. It's like the bread and butter of numerical computing in Python. Now, we'll assume we have some sequential data. It could be text, time series, anything where the order matters. For simplicity, we'll use a super basic example, predicting the next letter in the sequence hello. We're creating dictionaries to map characters to numerical indices. RNNs don't speak letters, they speak numbers. Okay, now we'll define our RNNs architecture. We need to specify a few key things. First, input size, that is, the number of features at each time step, and in our case, the size of one not encoded vector representing each character. The second is the hidden size, that is, the number of neurons in the hidden state. Think of it as a memory of our RNN. And the third is the output size, meaning the number of possible outputs. In our case, the number of characters in our vocabulary. So, if you're confused about one-hot encoding, it is just a way to represent categorical data as numerical data. For each data point we have in the vocabulary will be represented by a vector of size n, where n is the size of vocabulary and all the values will be 0 except the index associated to that vocabulary will be 1. Now for the fun part, initializing the weights and biases. We'll use NumPy to generate random values. Remember to keep these small to avoid exploding gradient during training. We'll talk about more on that later. We're multiplying by 0.01 to initialize the weights with small random values. U transforms the input, W transforms the previous hidden state, and V transforms the hidden state of the output. Time to implement the forward pass. This is where the magic happens. We'll iterate through the input sequence, updating the hidden state at each time step. hprev is the hidden state from the previous time step. We use tanh as the activation function. The softmax function converts the output into a probability distribution over the possible characters. But how do we know if our RNN is doing a good job? We need a loss function, right? So cross-entropy loss is a common choice for classification problem. We are essentially calculating the negative log likelihood of the correct class. The lower the loss, the better for us. Now here comes the tricky part. Backpropagation through time, or BPTT. This is how we calculate the gradient of the loss function with respect to the parameters. It's like unrolling the RNN through time and applying the chain rule. So buckle up. We start by calculating the gradient at the output layer, then propagate them backwards through the network. This involves a lot of matrix multiplication and derivatives, but don't be intimidated, just remember the chain rule. Now, we'll put it all together in a training loop. We iterate through the training data multiple times, or epochs, performing a forward pass, calculating the loss, performing a backward pass to get the gradients, and then updating the parameter. We use a learning rate to control how much we adjust the parameters each time. After training, let's see if our RNN can predict the next letter. Not bad for a simple RNN. You'll likely see ELLLL. With more data and training, it would be better. One thing to keep in mind is the vanishing exploding gradient problem. Because we're multiplying gradients through many time steps, they can either become very small, meaning vanishing, or very large, meaning exploding. This can make training difficult. The techniques like gradient clipping, LSTMs, and GRU are used to address those issues. And that's a basic RNN implemented in NumPy. It's a Simplified example, but it captures the core principles. Now, about that goldfish, if you remember, both RNN and goldfish have a limited memory. RNNs have a hidden state, but it can struggle with long-term dependencies. Goldfish, well, you know. So, if you found this helpful, give us a like and subscribe. Also, let us know in the comments what other tech topics you'd like to break down. And remember, keep learning.